In a universe far, far away, the USS Enterprise Dry Cast Expedition Force is planning to conquer the wet Castia galaxy. But wait, they've received a distress call from the advance team. The team feels disoriented. They've lost their way. Dr. Spock, can you explain what's going on?
Wetcast, drycast are both concrete. But when folks who know a lot about one venture off into another, things can start to feel weird pretty fast. In fact, you may feel like you have beamed up to a strange alien world. So, before we boldly go where only a few drycasters have gone before, a word to the wise. Take whatever you know about concrete and leave it on the USS Enterprise, 'cause it's not much use where you're going.
Thanks, Dr. Spock. Let's see if we can help them out with some background information. So how is wet-cast concrete made? As you've guessed by now, wet-cast units are manufactured from slump concrete, similar to the concrete that is delivered in ready-mix trucks, just on a much smaller scale. As you can tell from this wet-cast video that shows self-consolidating concrete, or SCC, we have to think about workability and flow in a very different way. Words like pouring and placing. And you're right, there's no equivalent for this kind of pouring in the dry cast world. In the wet cast production process, slump concrete is mixed and poured into a mold and then often vibrated to remove air bubbles and consolidate the wet mixture into mold corners and texture details. Note that if self-consolidating concrete is used, then no vibration is necessary. The concrete remains in the mold usually for 8 to 24 hours to cure or harden until it reaches a desired strength. The mold is then removed and the unit is packaged and shipped. As you might expect, dry and wet cast units don't look the same. The formable nature of wet cast concrete enables it to be placed into custom molds of different shapes and sizes and to show a variety of highly decorative surface finishes, ranging from smooth and elegant to granular texture details that closely mimic wood or natural stone. It's also possible to produce larger format units like steps and retaining walls that could not pass through a dry cast machine. Wet cast concrete can be more flexible in mixing, molding, and conveyance operations compared to dry cast concrete. However, due to the time needed for concrete to harden and cure in the mold, in wet cast operations, molds are used twice a day at the most. Bottom line is that wet cast units are easier to customize, but take longer to produce. Wet cast concrete concepts: strength, workability, and the water-cement ratio. Let's put our Captain Obvious hat back on here and state that since wet cast concrete is wetter, it will almost always have more water by volume in the mix. Wet cast folks spend a lot of time and energy on designing and managing the mysterious water-cement ratio. Hold on a second. Space Command says they've located Yoda wandering around on a distant planet. Maybe he can help us unlock the key to the water-cement ratio and save our mission.
Dry cast we've done for many years, yes?
It would be logical to add wetcast to our discussion.
Workable wetcast is more.
Affirmative. But there are considerations. More water is more workable, but it affects strength.
More water, stronger makes it.
My internal database tells us more water can actually make it weaker. The perfect water-cement ratio is 0.41534790.
Flow concrete does at that number?
Tests have proven that using chemistries will aid in flowability without lessening strength.
Speak with the High Ranger we must.
Scotty, beam up the High Ranger.
Do or do not, there is no try.
Thanks, Dr. Spock and Yoda. The water-cement ratio is calculated by dividing the mass of water by the mass of cementitious materials. Note that the term that is often used is water to cement, but this is taken to include other cementitious materials like fly ash or slag cement. So why is this ratio so important? Workability and strength are two fundamental performance properties for slump concrete. Same as in dry cast, strength is mostly influenced by the amount of cementitious materials, and all other things being equal, more cementitious materials will generally lead to higher strengths. In wet cast, it is possible to add more water than is needed to hydrate the cementitious particles, and this leads to a high water-cement ratio. When too much water is added, the excess water will bleed out, leaving voids and lower strength concrete behind. Before the invention of water-reducing admixtures, the amount of water in the mix impacted both the workability, or slump, and the strength of wet cast concrete. More water makes the concrete more workable, but it lowers the strength. So back in the day, concrete that was easier to place used to be associated with lower strength and durability. Nowadays, we use admixtures to control and optimize both of these performance criteria. But the water-cementitious ratio is still fundamental to the quality of the concrete. Add too much water and strength and durability will be compromised. This highlights a fundamental disconnect with dry cast concrete. In contrast to dry cast, where we always need to add as much water as possible to the mix, short of picking or pulling, to make quality wet cast, we are genuinely trying to take water out. And we know, you've always heard ACM going on about adding more water, but that's for dry cast. The wet cast world has a different set of rules. As you can see from the chart, as the water-cementitious ratio increases, the compressive strength decreases. If you take a look at the admixtures used in wet cast, you will see a heavy emphasis on water reduction. ASTM standard C494 covers several grades of water reducers that are used to deliver workability and strength performance needed for different engineering requirements, placement methods, and use conditions. Since the water content is so critical, it follows that moisture measurement and control is also critical. To have a reasonable chance of producing consistent quality wet cast, the water-cementitious ratio must be consistent day by day and mix by mix. This means it's essential to know how much water is going into each mix, so moisture meters and correct moisture compensation in the mix design for moisture present on the aggregates is essential. The cubic yard or cubic meter mix design volume. Unlike dry cast mix designs, wet cast designs are always designed by volume to produce a cubic yard or cubic meter of concrete. This standardization makes it much easier to compare mix designs and manage raw materials. That sounds like a great idea, you say. Why don't we do that in dry cast? It's complicated in that it's possible in dry cast, but the air void quantification is much harder, and it needs an in-depth discussion that we just don't have time for here. Here's an example of a wet cast mix design for a large retaining wall unit in a northern climate that requires air-entrained concrete. As always, this is for 1 cubic yard or 1 cubic meter of concrete. Note that the water-cement ratio calculation and the target entrained air content are included in every mix design. The actual air entrainment can be measured using ASTM C231 standard test method for air content of freshly mixed concrete by the pressure method. Freeze-thaw durability. Another important difference between dry and wet cast concrete is their use in freeze-thaw environments. Due to the dense nature of slump concrete, this concrete is vulnerable to freeze-thaw damage from water inside the concrete expanding as it freezes. This expansive force creates tremendous pressure on the concrete matrix and can result in a failure of the unit. Air entraining admixtures are used to develop microscopic air bubbles in the concrete that water can expand into as it freezes. In contrast, dry cast concrete typically has a void structure of around 8 to 12% by volume, so any moisture in the concrete has plenty of room to expand into. Controlling air entrainment in wet cast can take time and attention for the entire production crew. If you're in Florida, this won't be something you worry about. Up north, it can be a daily concern. Workability and slump. To be formable and to take the desired surface texture and details, wet cast concrete has to fill the form or mold. Slump test. The slump test is a measure of the consistency or workability of fresh concrete and is described in ASTM C143, standard test method for slump of hydraulic cement concrete. To do the test, fresh concrete is poured into a slump cone, the cone is removed, and the amount of slump is measured. The higher the slump, the higher the number, the more pourable and easier it is to place the concrete. Conventional ready-mix concrete slumps range from 2 to 8 inches. Self-consolidating concrete, or SCC, is measured by slump flow, which can range from 15 to 30 inches in diameter. For wet cast concrete production, flow has a big impact on how well the slump will take form details. Higher flow, sometimes even to self-consolidating concrete, means that texture and details of the form will be transferred to the concrete, as we see in this example of wood grain. Form release. The closest dry casters may come to this is when units adhere to boards and have to be hammered off to be packaged. For wet casters, just like when making a cake, if the form does not release, it's a mess.
Thanks for joining us on this journey to a new world. We hope that we have given you a useful introduction to concepts like water-cement ratio, workability, strength, and freeze-thaw. To learn more, please watch the follow-up wetcast video, where we take a practical look at wetcast concrete production. So live long and prosper.
Be sure to tune in to part 2 to meet the legendary High Ranger from the planet Canada Krita, the only Jedi better looking than Han Solo and tougher than Anakin Skywalker. See you then.